Hello and welcome back to Engineering 211 Statics, and I wanted to pick up where we left off last time working on internal loads and specifically shear and moment diagrams. We'll go back and look at that problem that we finished up with last time, but before we do that I would like to tackle a new problem, a probably just as common a problem, but a simply supported beam that has a distributed load on it. So that's what we're going to try now. Something like this. And we're going to say that this load is W. We use a couple designations on that. Sometimes we use W, sometimes we use Q, but your author will use W and I'll stick with W. And we're going to say that the length of this thing is L. So I need to come up with the reactions. I'm going to put the shear and moment diagram over here. So it looks something like this, where we'll have the shear and we'll have the moment. So the first thing I need to do is I need to come up with the reactions. So I have some R1 and R2 and R3, L between there. And then we have this distributed load, don't we? And we could say that that distributed load could be taken as a concentrated load in the middle that's equal to W times L, right? And it's going to be acting at the center line, which is L divided by 2. L over 2. Okay, so with that, if I were to sum the moments about the left-hand side, setting it equal to 0, I have WL times L over 2, that times that distance, minus R3 times L, and I come up with R3, solving for R3, it's equal to WL over 2, which hopefully makes sense. The entire load is WL, symmetrical, so each one of R2 and R3 would support half of it. We'll see that for R2. If I sum the forces in the vertical direction, setting that equal to 0, I have R2 plus R3 minus WL. We put this in for R3, and R2 becomes WL over 2. And of course, if we were to sum the forces in the horizontal direction, setting those equal to 0, we get that R1 is equal to 0. So now that I got the reactions, and there's never any shortcut to the reactions, you always have to get those. I'm going to take a section. I'm just going to take one section through here. I'm going to look at this section for X somewhere coming from the left-hand side. So we're going to say that X is between 0 and L. And if I did this, I'd have something that looked like this. And I've got to put the distributed load on there. And according to the deformation sign convention, the shear is going to go down like that, and the moment is going to go like that. I got to put those in so my diagrams are consistent. And then I found this reaction WL over 2, where this distance here is X. So if I sum the forces in the vertical direction, setting that equal to 0, I have WL over 2 minus V minus, this is W, so it's going to be WX, right? So W times X, that's the total load there. I'm subtracting that. I have to add that. So V is equal to WL over 2 minus WX. Or I could say, if I wanted to, that V is equal to W times L over 2 minus X. Okay, so we'll hang on to that. If I sum the moment about the cut point, this being the cut point, what do I come up with? So sum of the moment about the cut point, setting that equal to 0, I'm going to have M plus then W times X That's the area of this, and it would be acting again at the center of that. So this distance here is x over 2, right? So the distance of x over 2. So the area of this rectangle is w times x, that's the force, times the distance that it's acting through, that's that distance right there, which is x over 2. It's going to be acting at the center of that rectangle. And then I have to subtract off WL over 2 times the distance it's acting through, which is x. So I can solve for m. M turns out to be equal to WLx over 2 minus WX squared over 2. And you could say that this was W over 2 times LX minus x squared. And some people would recommend factoring on an x, which would be fine, but I think I'm going to leave it like this so we can be sure that we know it's a second order equation. Did I do that algebra right? I think so. So if we've got that, what's this diagram look like? Well, if I plot this thing for the shear, if I put x is equal to 0 in here, I get WL over 2, right? So I'll have WL over 2. And if I put x is equal to L in there, I have what? Minus WL over 2. And what kind of an equation is it? It's a linear equation. So I have something like that. Okay. And then, if I look at this moment equation, if I put x is equal to 0 in there, I have 0 minus 0, so I have 0. If I put x is equal to L in there, I get L squared minus L squared, so again I have 0. Now, where this crosses might be kind of an interesting point. So if I were to evaluate this, if I were to look at this with x equal to L over 2, and I haven't drawn this just perfectly, but this would be x equals L over 2. It would be in the center. What do we come up with? Well, we have W over 2 times L times L over 2 minus L squared over 4. Is that right? So what do we get out of that? So I have L squared over 2 W over 2 times L squared over 2, which would be 2L squared over 4 minus L squared over 4, which gives me in the bracket here, I'm just kind of using this as a scratch paper. Let's see, 2 of those less 1 gives me 1. So I'm going to end up with W L squared over 4 multiplied by 2 is 8, right? WL squared over 8. So I have a point here, WL squared divided by 8. Okay, we could plot some more points, and when we did, we'd have something that went like that, because it's a second order. Okay, so WL squared over 8. And that's a common one that comes up all of the time. Well, couple things before we leave this problem. Got a few more things I'd like to look at on this one. So folks might ask the question here, could we do the right-hand side? So what would that look like? Well, if I look at the right-hand side, I'm going to have, again, the right-hand reaction. That would be R3, which would be the same in this case, WL over 2. And then I'd have the shear going up and the moment going clockwise, according to the deformation sign convention. And then I still have this load like this, W. And the tricky thing here is that this distance is no longer x, but that distance is L minus x, isn't it? Okay. So when I go through this problem and I were to sum the forces in the vertical, setting those equal to 0, and sum the moment, setting that equal to 0, I would get the same result. So because this distance is L minus x, I would have a lot more algebra. You can go through that on your own if you want. You will come up with these exact answers, so it'd be a good trip through algebra for you. But you get a lot more algebra because of this not being a nice tidy x, rather being L minus x. The other thing that I would like to look at is I'd like to compare this to the one that we looked at last time, where we had a simply supported load like this. This one, of course, was 0. We had the load in the middle, P, and this was L over 2 and L over 2. Of course, we had then P over 2 and P over 2. And when we drew the shear and moment diagram, as we finished up last time, we had something that was like this. The shear jumped up, and then it jumped down. It was like this. This was P over 2 and minus P over 2. And then the moment did what? At the middle, moment went up like that, that being the center line. Went up to what? PL over 4? Okay, because this distance here was L over 2. And we noticed that the area under here was P over 2 times L over 2, PL over 4. Okay. It's also kind of interesting here that we had this reaction P over 2, and that's what the shear was there. And the difference between this one and this one is what? P, isn't it? Okay. So none of those are coincidences. So how does it work on this one? Well, a couple things that I should note is that this case is very different than this case. We could not model this by putting a concentrated load in the middle. Anyone that has maybe lived where it's really cold and they get ice and sometimes people fall through the ice realize that this example has very different loading than this example. While we might have a situation where the reactions might be the same, the internal forces in here, the internal stresses in this case would be different. Because going back to that ice example, when you try and rescue someone on the ice, do you walk out as a concentrated load on the ice? No, you don't. You usually lie down and try and distribute your weight. So we would expect the internal forces here in this case to be different, and all things being equal, less than this case. So I want to really stress that point. We do not analyze this distributed load by simply turning it into a concentrated load. You can see these diagrams are very different. Well, speaking of the diagrams, if I come back here and I look at the area under this, the area of this triangle, what's that going to be? Well, I'm going to have WL over 2 times this distance, which is L over 2, times a half, because it's a triangle, right? So what do I end up with? WL squared over 8. Okay. Interestingly enough, the reaction over here, what was R2? WL over 2. So we're starting to see some things that are kind of interesting. So I'd like our next move to try and illustrate those, and maybe we can come up with a shortcut method where we don't have to do all of this algebra. I think this sectioning and whatnot's important because we'll find that we can't always use the shortcut method, and of course it's the derivation for the shortcut method, but if we want to try and work these problems faster and faster, this shortcut method should be important. Last thing before we leave this problem here, again, if someone was wanting to reduce weight or to cut a hole, it looks like we have the majority of at least the bending in the middle, right? Although we have a high shear at the outside edges, so maybe someplace in here might be the best place for a hole or a notch or something like that. We can start to make those determinations with these diagrams, and they'll be very important when we look at strengths of material spring term. Well, with that, let's see if we can build that. Let me separate this. These are two separate things. So let's see if we can build that shortcut, come up with that. So to do that, my pen's getting kind of old. So to do that, I'm going to start out with a simply supported beam. And we could, if we wanted to, do this with a cantilevered beam. I'm going to stick with a simply supported beam. We could use a cantilevered. Let's say that's Y. This is X. I'm going to take some arbitrary load there. It could be constant, trapezoidal, triangular. Look at the load like that. And I'm going to come over here and I'm going to look at this section right there. And I'm going to say that this distance here is X. And then this little distance right here, you can see this coming. This is going to be delta X. So I'm going to pull that little piece out and see what it looks like. I'm going to cut that out and see what I have going on there. Well, having sliced that out, I'm looking essentially on this side. I'm looking like if I have a right-hand side of a beam. So I'm going to put the shear on like this, and I'm going to put the moment on like this. And then over here, it's like if I'm looking at a left-hand side of the beam, so I'm going to put the shear on here. The shear is probably going to change, so why don't I account for that? I'm going to say that's V plus delta V. And then over here, the moment will go like this, and it's probably not just M. I'm going to say that it's M plus delta M. Okay. Again, this distance over here is delta X. Delta X. And I'm going to take this load that's above here, this load that's in here, and I'm going to say that that's delta F, which would be equal to W of X times delta X. If this is W of X, our load, and we multiply it by delta X, we get that value, and then as delta X, and we're going to take it to our limit, but as it gets smaller and smaller, we can think of that as a rectangle. In terms of the area. Now, if it's a rectangle, it's going to act at the middle. If it's a triangle, it might act to one side or the other. So let me look at this distance here, and I'm going to say that this distance is epsilon times delta X. Okay, and hopefully that will work. If epsilon is equal to a half, I'd know it was a rectangular load. If epsilon is equal to a third or 2/3, I'd know that it's triangular. That should give me something to work with. So with that, I can talk about summing the forces in the vertical direction, setting those equal to 0. And what do I have? I have V acting up. And then I have to subtract off this one, W of X times delta X. Anything else? I need to subtract off this one. So I'm going to have minus V minus delta V, because I'm subtracting off that. I think that's it. I've got that one, and that one. So if I look at this, I can say, let's see, I get to cancel that term with that term, and I can say that delta V is equal to minus W of X delta X. Yeah. Or that delta V over delta X is equal to minus W of X. And I'm going to, like you probably did many times in calculus, take the limit as delta X goes to 0. As delta X goes to 0. And I come up with dV over dx is equal to minus W of X. Okay. Well, what's that say in plain English? Well, in plain English, what's that is telling us is that the dV dx, that's the slope. Slope of the shear diagram. That the slope of the shear diagram is equal to what? is equal to negative the value of the load. Okay, so that could be useful. The slope of the shear diagram is equal to negative the value of the load. Well, if I continue on and I sum the moment about the cut, and I guess we have two cuts, so I should probably be a little more specific. I'll say O there. So summing the moments about O, setting that equal to 0, what do I come up with? Well, I'm going to have this shear force actually intersects that point. I've just drawn that off for clarity, but this one doesn't. So I'm going to have minus V times delta X. Looks like I'm taking counterclockwise as positive. So this force here times that distance. And then I'm going to have to subtract off M, but I get to add M plus delta M. This one's positive, that one's negative. So I've taken care of that one, I've taken care of that one, I've taken care of that one. I have to add to it, I'm going to add to this thing what? W of X times delta X times the distance that acts through, which is epsilon times delta X, right? Epsilon delta X. So I get to do some canceling here. I can cancel those two, plus and minus. And when I get done with that, what's delta M? Solving for delta M, I get that delta M is equal to V delta X minus, so that term there, that went to the other side, and then I'm going to have a negative W of X times epsilon times delta X squared. So I could say then that delta M over delta X is equal to V minus W of X times epsilon times delta X. So again, I'm going to take the limit here. As delta X goes to 0. So doing that, I get dm dx is equal to v. And people might go, well, where did this go? Well, that went to 0. This is a higher order term, isn't it? That's why I was a little flippant or careless about epsilon, because I knew it was going to go away, this higher order term. So that drops off. What does this say in plain English? It says that the slope of the moment now is equal to what? The value of the shear. Slope of the moment is equal to the value of the shear. So those are going to be two important relationships for us. Well, I'd like to come back to this one here and this one here and do a little more work and see if we can find some area relationships. So let's do that. So with this at hand, I'll copy this down. I've got dv is equal to, taking this, just multiplying both sides on this one. So I'm taking this thing right here, multiplying both sides by dx. So I have minus w of x dx. And I'm going to do a similar thing here. I'm going to say that I have dm is equal to v dx. So dm is equal to v dx. Okay, so those came from our previous work. Let's see what I can do with these. If I integrate both sides, I could say that delta v, the change in v, is equal to minus the integral of w of x dx. And if I do the same thing here, I could say that delta m m1 minus m2, the change in m, is equal to the integral of v dx. So again, what's this say in plain English? This one is that the, let me make sure I got that right. Yeah. Yeah, okay. So this one is the change in the shear. The change in the shear is equal to negative. We've got that negative sign we brought out of the integral. Negative. What's that? We think of the integral as the area. This is the area under the load, isn't it? Okay, so the change in the shear is equal to minus the area under the load. Whereas this one, the change in the moment, these are separate, we're just doing them at the same time. Change in moment is equal to what? The area under the shear, isn't it? So I have that the change in the shear is equal to minus the area under the load, and that the change in the moment is equal to the area under the shear. Okay, so between these and these, we should be able to draw the diagram much quicker. Now, other things that we probably want to think about for our shortcut. We want to work from left to right. Okay, so we're going to work from left to right, just like you read in a lot of languages, not all languages. Work from left to right. And sometimes we'll cheat on this. As we get started with this shortcut, we're going to follow these rules very carefully. Once we get more comfortable with it, we can maybe cheat on some of the rules. And maybe if there's something in the middle that I don't want to tackle, I'll work from the left to that point, and then maybe I'll come over and work from the right backwards to that point. But you got to be pretty good not to get in trouble with that. We're going to start and end at 0. Okay, which is really nice. If I don't get back to 0, I know I've made a mistake somewhere. So these are kind of, they indicate the correct answer, because if you don't get back to 0, you got a problem. Then what do we do with concentrated forces? So concentrated forces, if I have a upward force, and this could be a load or this could be a reaction, we're going to treat them the same. So if the force is up, I have an upward jump in the shear. If it's a downward force, what do you think? Downward jump. It's a downward jump in the shear. Okay. And finally, we don't have these a lot, but when we do, you got to be real careful with them. Concentrated moments. So a concentrated moment, how do we handle those? If the moment is clockwise, we have an upward jump. An upward jump in the moment diagram. If the moment is counterclockwise, we have a downward jump. Okay, so if it's counterclockwise, we have a downward jump. If it's clockwise, we have an upward jump. This is probably a little more intuitive. Up, we jump up. Down, we jump down. This one, you just have to remember this. And I always think about, on a Friday afternoon, clockwise, that's probably a positive thing. Let's keep that clock going around till 5 o'clock, or however you want to think about it. But that is a upward jump. Counterclockwise, downward jump. Okay. One thing to note here, do concentrated forces show up on the moment diagram? Not directly. Do concentrated moments show up on the shear diagram? Not directly, but they do affect the reactions, so they're probably going to show up indirectly, but not directly. We're only going to be jumping with forces on the shear diagram. We're only going to be jumping with moments on the moment diagram. Well, that gives us a great advantage when we start to look at some problems. Let's go back and tackle those problems like we have started with. So let's say that we have a simply supported beam, concentrated load in the middle. Okay, and you got to get the reactions. There is no shortcut for the reactions. You have to get the reactions, and you have to get the reactions right. So must find reactions. Okay, and they have to be right. We found that this was P divided by 2, and this was P over 2. I'm not going to go back through that. You go back to the last lecture and see what we did on that. But once you've got those reactions, then you can very quickly go through this shortcut. So here's our shear. What are we going to do? We start at the left-hand side. We start at 0. All of a sudden, we come to this upward force. So we jump up, P over 2. And then what do? A lot of people like to jump back down. Well, you don't do anything. So we just continue on, steady as it goes until we get here. And then what? We have a downward force of P. So if we are at P over 2, and we subtract P, what does that give us? Minus P over 2, doesn't it? So we're jumping down to there, to minus P over 2. And then steady as it goes. We get over there, then we get to jump back up. We could even put these arrows in here where we're jumping up and we're jumping down. That's it. Okay, that's our shear diagram. It's that fast. How about the moment? Well, the moment, I don't have any concentrated moments, so I'm not going to be doing any jumps. I'm going to start there, and I'm going to look at the area. What's the area under this thing? Well, it's P over 2 times this distance, which is L over 2. Which gives me PL over 4. So I'm going to start at 0, and I'm going to end up at PL over 4. How do I get there? Well, I've already used that the change in the moment is equal to the area under the shear. I found the area under the shear, then that's my change in moment. Then what do I know about the slope of the moment? The slope of the moment is equal to the value of the shear. This is a constant positive value, so this should have a constant positive slope. Now, if I look at the area here, what's that area? Well, minus PL over 4. It's below the line, so that's why we take it as a negative area. So if we're at PL over 4 and I subtract PL over 4, that takes me back to 0. How do I get there? Well, this has a constant negative value, so it will have a constant negative slope. Okay? Very quickly. Now, some people might say, well, you don't have an equation. I would agree. I do not have an equation. So they might say, well, what is the value? Let's say that I want to put a hole right there. So I want to know what the value of the moment is. And I would say it's the area right there. Okay? So you can get a lot out of this, and you do it quite quickly. So the shortcut is very good. It's important to remember how we got the shortcut by doing a section. We had to take 2 sections on this in the past, but it's much faster to use the shortcut if you can. Sometimes you can't use the shortcut, and we'll talk about that in the future. Well, let's try the last one for the day, and that's to repeat what we started the day with. So if we look at the PDFs, it won't look like that we got very far, because we'll start with this. So that's W, and we have L. And again, you got to get the reactions. If you're still having trouble getting the reactions, you got to practice, practice, and practice, because you got to get those right. WL over 2, WL over 2. If you need help with that, you can go to the first part of this lecture, rewind the lecture, and look at that. So you got to get the reactions. There's no shortcut for the reactions, and they have to be right. We were basing the shear diagram on these reactions. We were basing the moment diagram on the shear diagram. So if you don't get the reactions right, everything's amiss from there. So get the reactions. I'm not trying to say the reactions aren't important by not going through this, but you have that at the beginning of the lecture. So if we look then at the shear, what do we have? We come along. We start at the left-hand side. We start at 0. All of a sudden we jump up. WL over 2, right? And then what happens? Well, we've got some load under there. We better take that into account, right? Better get my pages back here. What's it say? That the change in the shear is equal to minus the area under the load. Change in the shear is equal to minus the area under the load. What's the area? W times L. Put a negative sign in front of it, right? So if I am at WL over 2 and I subtract WL, what does that give me? Minus WL over 2, right? So I'm down here at minus WL over 2. How do I get there? Well, it says that the slope of the shear is equal to minus the value of the load. The load is a constant positive value. So I have a constant negative slope. Now I'm sitting down here at minus WL over 2, and then I have this one that jumps up, so that gets me back to 0. That's good. I can be quite happy with that. We can finish this. And this one's fairly obvious to see where it crosses. Sometimes it's not so obvious. You just use similar triangles. You could say that this distance is x, and this is L minus x. So by ratio and proportion, you would say that WL over 2 is to x as WL over 2 is to L minus x. That's using a similar triangle there and a similar triangle there, because this angle and that angle is the same, right? So that's how you would find that if it didn't cross at an obvious point, and sometimes it doesn't. Okay. Well, because this distance is important, it's important to know that this crosses at where it crosses. In this case, it crosses at the middle, because I need that to find the area. So when I do the moment, I start at 0. I start at the left-hand side. This has some area. What's that area going to be equal to? Well, WL over 2 times this distance L over 2 times a half, because it's a triangle. What does that give me? WL squared divided by 8. Is that what we started our day with? WL squared over 8. And how do I get there? Well, it says that the slope of the moment is equal to the value of the shear. Slope of the moment is equal to the value of the shear. We have a large positive value, so I'm going to have a large positive slope. I have a small positive value, so I have a small positive slope. So it'll just go in just like that. Okay. Now, what about this triangle? It's the same thing, except it's negative, right? Okay. So that gets me back to this point. How do I get there? Again, I have a small negative value, so I'm going to have a small negative slope. Then I have a large negative value. I'm going to have a large negative slope. And I'll put that in just like that. Now again, people say, well, you don't have an equation. But if I want to know the value right here, what do I have to do? I just have to go up here and find the value of this trapezoid. Okay. Now, where this shortcut method begins to break down is if you start to have higher order curves up here. If you have a second order curve here, then you're trying to find the area under a third order curve or something, and at that point a section might be the way to go. But in a lot of situations that we use in engineering, situations like this, situations like the previous one, where'd my previous one go? Right here. The shortcut method works really well. I mean, we did these in a fraction of the time that we had done them in the past. But again, you got to get the reactions. There's no shortcut for the reactions. You got to get those. Once you've got those, you can hammer through this shortcut pretty fast. So grab some of the homework problems for Shear and moment diagram. See if you can do them with sections. See if you can do them with shortcuts. We've got a couple more problems in this. We'll be wrapping this up in the next lecture and moving on to the next section, which is friction. So thank you for watching, and take care till then.